Given us want to partition string into as many parts as possible, each letter appears in at most one part. Return a list of integers representing the size of these parts. Mm. Okay, so if we run through this and put everything in a dictionary, I mean the indices of all these in the dictionary would show that all of ABC is 9 or less, or yeah, but we don't. How do we know 9 or more doesn't include, you know, any of ABC? And how do we know like C is like the last thing we absorb? As many parts as possible. Hmm. 9. What is 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's just saying ninth character 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I see. If letter not in view table, then we want to initialize this with the current index. Okay. Now, if it is in a table, we've already got this entry, and we like this. And now we get a table of all these indices, and so we know this is in order. So this would maximum index of, so let's say we have this A, the table will have 0, 1, 0, 2, 3, 4, 5, 6, 7, 8, for example, as a maximum index, and that's kind of the minimum viable index. So for example, suppose I partition here, we know A would occur sometime after this letter C, so we can't do it. We can do A, and that's the minimum viable, because you look at this case, E is the minimum viable, but for all the letters in between, we also need to make sure that it's actually less than the minimum viable, otherwise we need to increment our minimum viable. So the beginning are min viable are -1. So for letter in S, this is a maximum index, and then we say, well, temp viable if temp viable. So let's say we do E, and then we get this index. This will update this min viable to this. And then now for the next letter C, we want to see that it's if the min viable for C is going to be bigger than this, then the min viable is going to be this index here. I'm going to need to do a +1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and what? What about this? 0, 2, and then this is 8. Okay, so in B, I'll find that the maximum B is actually less than the min viable, so I will update the min viable. Okay, so I'll reset the index here, and then so for B, I'll find that it's not, and then A, it's not going to be greater than. B, again, it's not going to be greater than. We're going to go all the way up to C. And so if my index is going to be this min viable, actually I want to just add one at the end probably. So if I'm at the final one, min viable, if index is min viable, then go ahead and append this index. plus 1. So in this case, 9. 10, 8. There's an x 0, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15. So 15 is 9 plus 7 minus 1. Okay, so if I'm at this A, then I'll append this 9 and reset to 0. Actually, I need to reset to -1 because I want to do this and start at 0 on the next letter. So 0, 1, 0, 1, 2, 3, 4, 5, 6, and then 6 plus 1, 7. Let's see if this does anything interesting. Gets the first one. Index is -1. Also need to reset this min viable. Right, so if I'm at D, yeah, I can't do this because the index is based on the 0, so I actually just need to do some subtraction. So in this case, it's like the 15. So out -1. So my index would be like 15 for min viable. So that means my index is 15, 16, minus 9 is 7. I'll just sum it. I'm not gonna optimize this. But if it's 1, partition is 1, right? So Okay, so it looks like it works for that one. So if length of s is 1, return 1. So this is special case versus only one instance of C. Okay, so we skip this first time around, and then we do this. Our index is 0. So maybe it's a sequencing issue here where we want to know what the min viable is. In this case for C is 0, and then go ahead and check if we're already there, which won't miss this case. Now what about EE? What about, I don't need to test the one case because for the one case, it's a fixed return. I just finally want to test out the other case. Okay, looks good to me, and we're done.